Hello friends! In this video, we are going to write a C++ program to find the area of a triangle. Sounds simple, right? But there is more happening underneath than you would think. We will walk through the math, the code, and the quiet little detail most tutorials skip. What your computer is actually doing with those numbers when it computes square roots and stores decimals. Let's get into it. There are two formulas most people learn for the area of a triangle. The first one is the classic 1/2 times base times height. Clean, fast, but it only works when you actually know the height. The second one is Heron's formula. It works for any triangle as long as you know the three sides. You compute something called the semi-perimeter, that is just half the perimeter, and then plug it into a square root. We will use Heron's formula in our program because it is more general. Let me show you why it actually works. Here is the interesting part. Heron's formula does not need the height of the triangle at all, and that is unusual because every other area formula you have seen depends on height. What Heron figured out, almost 2,000 years ago, is that the three side lengths alone carry enough information to lock the shape of the triangle completely. Once the shape is locked, the area is fixed. The semi-perimeter is just a clever way to combine those three sides into a single number the formula can work with. That is why this one formula handles any triangle you throw at it. Before we write any code, let's lay out the plan. Every C++ program follows roughly the same shape. First, we include the headers we need. That is how we pull in features like input, output, and the square root function. Then we have the main function, which is where execution begins. Inside main, we'll read the three sides from the user, compute the area using Heron's formula, and print the result. 4 clean steps. Let's start writing it. First, the headers. We include iostream because we need to read input and print output. Then we include cmath, which gives us the square root function, and we will need that for Heron's formula. The third line, using namespace std, is a shortcut. It lets us write cout and cin directly, without prefixing them with std every time. Now we are ready to write the main function. This is the main function, the entry point of every C++ program. When you run your code, the operating system looks for main and starts executing from inside its curly braces. The int in front means main returns an integer when it finishes. Returning 0 is the standard way of telling the system everything went fine. Anything non-zero usually signals an error. Right now main is empty. Let's fill it in. Now we declare the variables we will need. 3 sides, A, B, and C, the semi-perimeter S, and the final area. All 5 are declared as double. A double is a 64-bit floating point number, which gives us a lot of precision for decimals. When you write this line, the program reserves 5 small slots in memory, 1 for each variable. They are empty for now, just waiting for values. Next, let's actually read those values from the user. Here is where we talk to the user. Cout, written as cout, sends text to the screen. It is short for character output. We use it to prompt the user for each side. Then cin, written as cin, reads whatever they type and stores it into our variable. Notice the direction of those little arrows in the code. Cout flows data out to the screen. Cin flows data in from the keyboard. 3 prompts, 3 reads, and now A, B, and C hold the user's numbers. This is the heart of the program. Line 1 computes the semi-perimeter, A plus B plus C divided by 2. Line 2 applies Heron's formula directly. We multiply S by S minus A, by S minus B, by S minus C, and then take the square root of that whole expression. The sqrt function comes from the cmath header we included earlier. In 2 lines, we have turned the formula on the slide into working code. Now we just need to print the answer. And finally, we print the result. Cout sends 3 things to the screen, one after the other. The label area equals, then the value stored in our area variable, and then endl. Endl just means end of line. It moves the cursor down so the next output starts fresh. For a triangle with sides 5, 6, and 7, the area comes out to roughly 14.7. The program is complete, but there are a few things happening underneath that are worth a closer look. Here is something most tutorials skip. When you call sqrt, your computer is not pulling the answer out of a magic table. It is running an iterative algorithm. It makes a rough guess, checks how close it is, and refines the guess again and again until it is accurate enough. On modern CPUs, this happens in dedicated hardware in just a few nanoseconds. The reason this matters, the result is almost never exactly right. It is a very, very close approximation. Which leads us straight into the next topic. We used double for our variables, but we could have used float instead. Here is the difference. A float uses 32 bits of memory and gives you about 7 digits of precision. A double uses 64 bits and gives you about 15 digits. For something like Heron's formula, where we multiply several values together and then take a square root, those extra digits matter. The errors compound. That is why doubles are the safer default for any real math. Float is fine for graphics and games, where speed matters more than the last decimal. Got it? Let's move on. Now look at this. Our program will happily accept any three numbers the user types in, but not every set of three numbers can actually form a triangle. There is a rule from geometry called the triangle inequality. The sum of any two sides must be greater than the third side. Sides 3, 4, and 5. Perfect. That is a valid triangle. But sides 2, 3, and 10, impossible. Two short sides cannot stretch across a long one. If the user enters bad values, Heron's formula will try to take the square root of a negative number, and your program will return something nonsensical. We need to handle that. Here is the fix. Before we run the formula, we check all three pairs with an if statement. The two ampersands you see, that is the logical AND operator. It means every single condition must be true for the code inside to run. If even one fails, we jump to the else block and tell the user the sides cannot form a triangle. This is a small change, but it is the difference between a program that crashes on bad input and a program that handles it gracefully. Always validate before you compute. Let's see it in action. First test, sides 7, 8, and 9. The program checks the triangle inequality, passes, runs Heron's formula, and gives us an area of about 26.83. Clean result. Second test, sides 2, 3, and 10. The check fails immediately. 2 plus 3 is only 5, way less than 10. The program does not even try to compute the area. It just tells the user, this is not a triangle. Same code, two completely different paths, and no crashes. But there is one thing about that 26.83 that deserves a closer look. Here is a quirk every programmer eventually runs into. In binary, your computer cannot store 0.1 exactly. So when you compute 0.1 plus 0.2, you do not get 0.3. You get something like 0.3, 0.00000000000004. That tiny extra bit at the end is a rounding error. It is harmless most of the time, but it has one big consequence. Never compare two floating point numbers using double equals. They might look the same on screen but differ by 1/10 underneath. For our triangle area, the result is accurate enough, but the lesson is universal across every language that uses floating point math. Heron's formula is great when you know the three side lengths. But what if you have something else, the x and y coordinates of the three corners? There is a faster formula for that. It is called the shoelace formula, and it works purely with the coordinates of the vertices. No square root, no semi-perimeter, just a few multiplications and a subtraction. This is the formula graphics engines and game engines actually use, because they always store geometry as coordinates, not as side lengths. Same answer, different shortcut, and a lot faster on a CPU. This little formula is everywhere. In 3D graphics, every model you see on screen, every character in a video game, every product in a 360 view is broken down into thousands of tiny triangles. The engine computes areas, normals, and angles on each one, dozens of times per second. Game physics engines use triangle math to detect collisions. CAD software uses it for engineering drawings. Even Google Maps uses triangulated meshes to render terrain. The same formula we just wrote in 12 lines of C++ is running, in some form, inside every modern engine. A few traps to watch out for. First, declaring the sides as int instead of double. The user will type 5, and your area calculation will silently chop off all the decimals. Second, integer division. If your semi-perimeter line divides by 2 and the sides are integers, C++ will throw away the fractional part. Always use 2.0 to force floating point math. Third, forgetting to include cmath. The sqrt function will not exist, and your code will not compile. And finally, skipping the triangle inequality check. We just covered why that matters. Small mistakes, big consequences. And that is the whole picture. We started with a simple question. Find the area of a triangle, and ended up touching geometry, code structure, validation, floating point precision, and even how 3D engines work. Heron's formula handles any triangle from just 3 sides. Use double for accuracy. Always validate the input before you compute. And remember, every modern game, map, and 3D model is built from millions of these little triangles. If this video helped, hit like, subscribe to Weberdoc, and drop a comment with what you want me to cover next. See you in the next one.